Hello, welcome back. And so just picking up as to where I left off in the first segment, we're looking at the dynamic recovery in this case. And I had indicated to you how these microstructures and how our understanding as to the underlying physics, the metallurgy as to what was taking place is very detailed and can be very detailed. However, it requires a lot of time. And indeed, if we take it a step further, we look later on, during the process of the dynamic recovery of that steel, then we see a further change in terms of the grains, the subgrains, and the intensity of that. So we can see this evolution, if you like, of microstructure. We can experimentally measure it, but the moral of the story is that it takes a lot of time. And not only does it take a lot of time, but at the end of the day, our knowledge as to what is happening is limited to a particular composition, but also a particular composition processed by some set of parameters. And indeed, if we look at the similar behavior in the case of recrystallization, we can do similar types of experiments, namely looking at the evolution of microstructure. And so in this case, we can see the evolution of subgrains or microbands developing as we deform the austenite. And we can see how that evolves. And indeed, schematically, I'm depicting what takes place in terms of the dynamic recrystallization process. We can extend this microstructural characterization, and we do. And numerous groups throughout the world have spent many hours on this. We can have similar examples for both static recovery, static recrystallization. I've already given examples in other modules for this course in terms of grain coarsening. I've given examples in terms of precipitation, but there are numerous other examples which we can draw upon from the literature. Not to mention the various types of phase transformations that would result. The point that I'm trying to make here is that we have done a lot of detailed characterization of the microstructure. And that's all well and good. But it is limited. It is limited in that the understanding that we develop is for a particular composition, a specific set of processing steps. If we deviate either from the standpoint of processing or composition, then of course it's natural to think that the microstructure would also deviate. And so we need to develop a better approach, certainly from the standpoint of our steel plant, in terms of being able to control the process, so that that process can deliver us a microstructure and corresponding set of properties that is right, not just the first time, but each and every time thereafter. So the first type of model that I wish to discuss is one that doesn't give us a lot of metallurgical understanding as to what's happening. However, it's quite heavily used in industry, and it's used in industry because it's based upon a lot of data gathering, and as a consequence of that, the overall accuracy is high. Generically, we refer to these types of models as a black box approach. Right? Think back to maybe when you were a child and you would go to maybe some museum my images of this natural history museum where they had a series of boxes, yeah, and the idea is you would put your hand into a box, and you couldn't see what was inside the box, yeah, but you would put your hand inside the box, and you would feel around for what was in the box, yeah, and obviously you did this quite nervously because you you didn't know what to expect, and you would have to sort of describe by your touch, what that was in the box. I refer to that as a black box sort of approach to modeling, right? And so this class of models where we don't have a lot of understanding as to what's in the model or why the model necessarily works, but we just simply know that it works and it gives us an answer, yeah. And so that answer often, because it's based upon a lot of statistical data, is quite accurate. That's a black box approach, right? Very little understanding, a lot of accuracy. The classic example of this type of model is an artificial neural network. So one such approach to an artificial neural network is to simply take some known quantities in a steel, such as chemical composition or processing conditions, and take that wealth of data that comes from our plant and put that together to give us a prediction of properties. Now, we have to be careful when we talk about prediction of properties. The easiest type of property to predict is that based upon strength. So things like yield strength, tensile strength, they're quite easy to predict. Why? Because we have very small statistical variation in their properties to begin with. For example, if you consider, you take a steel, some composition, and you perform a tension test on that steel, right? So from our tension test, we can get a measure of the yield strength, the tensile strength, the overall level of elongation or ductility. And if we test, say, 10 tensile specimens for one composition, we would see very little statistical scatter amongst measurements such as the yield strength or the tensile strength. Whereas the scatter may be higher, and it will be higher, in terms of measurements of ductility, elongation to failure, reduction in area, or indeed, even if we, instead of tensile specimens, if we had produced compact tension specimens for the measurement of fracture toughness, we would see wide variation. Again, statistically, that's understandable. That is, the fracture behavior is going to be more statistically scattered than will be properties of strength. So when it comes to modeling, it's not surprising that the models for strength prediction are going to be more accurate than those for ductility or fracture toughness. So as an example, in the case of our steels, so as some heat treatments, we may be interested in steels and a group of steels that we had processed in a way that we had subjected them to a quench and temper treatment. So what do we have? We have the steels which are re-austenitized, and we re-austenitize at some particular temperature, right, based upon some composition for reasons that I've already discussed a few modules ago. We then quench. Well, then the question becomes, well, how do we quench? What's the cooling rate? What's the quenching medium? Is it water? Is it agitated water? Is it oil? Is it agitated oil? Is it air? So we have these number of variations. After quenching, then we take that martensitic structure and we temper it. And the question becomes, well, what temperature do we temper? How long do we temper at temperature? Are we doing a single temper? Are we doing a double temper? So we have all these issues to contend with. And then finally, how do we cool from the actual tempering treatment? So we have a large number of process variations due to chemical composition variations, the thermomechanical treatment, the austenitization heat treatment, as well as tempering treatments and associated quenches, the geometry of the bar, which I have not discussed. Are we talking about solid bar? Are we talking about pipe? We have a number of these issues. If we're talking about pipe, then what's the thickness? What's the wall thickness of the pipe? On top of all of that, then we have measurement errors. So how accurate are we in terms of our temperature measurements, our measurements in terms of wall thickness, our control operator errors. What time of the year was the steel fabricated from the plant? What shift? Was it shift 3? Was it shift 1? We have a large number of variations that take place. But of course, one of the beauty of the data from the steel mill is that, we have a wealth of data. We have a wealth of data to put into such a model so that we can go back and, in spite of all these variations, we can quite reasonably predict properties. Here's such a prediction, right? So in this case, it's a plot of a predicted tensile strength plotted against actual measured yield strength, tensile strength data. Right? And so this data comes from my colleagues here at the university, but in the Department of Automotive Control and Systems Engineers, where they've developed an artificial neural network for a series of steels, and you can see we have quite good predictive capability between what was predicted by the model and what was measured. Right? So perfect prediction would be along this 45-degree line, and you can see we have pretty good predictive capability. So this gives us a very high degree of confidence. We have some scatter, as you would expect, but nevertheless, it's a model that we can be comfortable with. Now, the critical thing is on these sorts of models is we can use them for interpolation as to what's taking place here, particularly where we have areas of sparse population of data. We can fill that in, and it's quite good. We can be quite confident in the model, between the boundaries of the data where the data falls in that model. The danger of using such a model is to extrapolate on one side or the other of the model, because then you begin to get into danger there. So we have a model that we can be satisfied with. It gives us a very high confidence limit as to what's taking place. However, we don't really have an appreciation as to physically what's taking place. We simply know that, look, this is what we measure, and it agrees pretty much to what the model is predicting should be the case. And how does it work? Well, all those composition or process variables that I had alluded to, right, they all act as input values. And so this is where the degree of complexity of the model is either great or small. So the more information that we put into the model, the more data that we have, the better the model will be in terms of variability. So we have information relating to composition, to heat treatment, to quenching medium, to all of these parameters that we discussed. We take it into an algorithm to process and delineate the important variables to those that are less important. So there's a ranking, if you like, and then we can get outputs from that model. And the one output that I showed to you is in the form of tensile strength. If, on the other hand, we're interested in another output variable, such as ductility or fracture behavior, or indeed something like transformation behavior, then we can do that as well. So again, another way of looking at this is we have a certain number of inputs that go into the model. Obviously, as these number of inputs increase, the complexity of the model increase. We then take those inputs and we sort of give them a weighing. We rank them. So this is where we have our algorithm to process the data. There may be more than one sort of layer in which this processing takes place. But eventually, we arrive at outputs and with associated confidence limits in those outputs. So to recap on what we discussed in terms of artificial neural networks, they are very good for nonlinear data. They're very good for us so that we can learn from the data, so we can sort of look at trends in which that data is indicating. However, the trends that we see are mainly going to be functional, and they're not going to be structural. That is, they're not going to tell us that, well, it's this grain size that's given up. It's not going to be of that detail. It's going to be functional knowledge that we gain. So we need to be careful in terms of that. And also, the other point that I made is that the data should be used for interpolation only, right? And furthermore, we need to be wary of areas where we have high populations of data, where, of course, the confidence limit will be highest, as opposed to those areas which are least populated, in which, again, should be treated with some degree of caution. One other example of an artificial neural network, of an output of an artificial neural network, is in the form of transformation. And this data comes from Van der Zog, the group in the Netherlands, which shows output from a neural network in terms of transformation behavior and in terms of how that transformation behavior of the steel changes with, for example, carbon concentration, manganese, or molybdenum concentration. And so in all cases, we have a plot of temperature versus the logarithm of time in the usual way, looking at how the transformation start of, say, polygonal ferrite or pearlite or bainite or martensite sort of change as we change compositional variations. And so this is sort of a step up from sort of modeling for properties alone. And indeed, this brings us to the last illustration in terms of a artificial neural network and the sort of strategy. We started off with a composition coupled with processing sort of variables as input, but we can likewise have microstructure as an input as well in terms of the transformation behavior to predict then subsequent properties at the end of the day. So I think this is a good place to stop. I think we've concluded everything I need to say in terms of this black box approach to modeling. Now I want to begin to look at a completely different modeling strategy or series of strategies, and I'll talk to you then. Okay, bye.